Okay, so today we're going to pick up with the Phanerozoic Eon. So hopefully you guys will remember that we have different names that we give to the different periods of time in geologic history. And the periods of time are kind of nested. So eons are these big, long periods of time. And then the big, long periods of time can be broken up into eras. Eras can be broken up into periods. Periods can be broken up into epochs. So the Phanerozoic Eon is the most recent eon in geologic history. It dates back to 542 million years ago and goes all the way up till today. And the word Phanerozoic Eon means visible life. So while we know that there are life forms that were around quite a long time before the Phanerozoic Eon started, a lot of the kinds of fossils that we think about as being evidence of past life, that are large-sized organisms, are things that have existed during the Phanerozoic Eon. And so that's where it got his name from. And if we're thinking more about our 24-hour clock, then the Phanerozoic Eon would start about 9:20 p.m. On our day. So a lot of geologic time has already occurred before this time period starts. And the Phanerozoic Eon can be broken up into 3 eras. The first era is the Paleozoic Era, which means ancient life. Then the Mesozoic Era, which means middle life, and Cenozoic Era, meaning recent life. So we'll talk about all 3 of these eras. And each of the eras can be further broken down into periods. And so the first period in the Paleozoic Era is called the Cambrian. So the Phanerozoic Eon and the Paleozoic Era and the Cambrian period all start at the same time, 542 million years ago. And as a result of that, a lot of times people refer to the periods of time and rock formations and certain kinds of fossils that occurred before 542 million years ago as Precambrian. That's a common term that you will run across in geology. And so that's what that refers to. Everything that we've talked about so far is Precambrian, and now we're starting to begin at the Cambrian and move forward from there. And then there are other periods, the Ordovician, Silurian, Devonian, Carboniferous, and Permian, and then others that we'll talk about a little bit more in today's lecture. Okay, so the end of the Proterozoic Eon, we discussed last time, occurred when the Earth became very, very cold and was either nearly completely frozen or completely frozen over, depending on whose theory you think is correct. But the Earth was in the snowball Earth state, and we talked about the fact that that is a very difficult and extreme environment for organisms to survive in. And so there were huge extinctions that occurred where many organisms that had evolved during the Precambrian died off right at the end of the Proterozoic Eon. So as the snowball Earth melted out, we mentioned this occurred because of the increase in greenhouse gases due to volcanic activity, warming up the Earth. The Earth is almost like a blank slate. There's not that many organisms there, and we embark on what both biologists and geologists refer to as the Cambrian explosion. So the Cambrian explosion takes place for about the first 20 million years of the Paleozoic Era or the Cambrian period, and during this period there's a huge explosion in the kinds of living organisms that are present. There's a very fast evolutionary change, and many, many different kinds of organisms are starting to evolve kind of in this blank slate where there's lots of growing space around the world that's available. There's not a lot of competition because so many organisms were previously wiped out. And in addition, the conditions are pretty conducive to life. So as the Earth starts to warm and warm, the ocean increases in elevation, and the ocean increases so much in elevation that it comes up over a lot of the continental area and creates these kind of shallow seas that then, because they're shallow, can get quite warm, that are pretty plentiful with oxygen, and that kind of condition is very conducive to life. And so lots of organisms thrive, do well, continue to evolve, and start to explode. So if you look at the diagram at the bottom of the slide here, you'll see that at the very beginning of the Cambrian, there's all these purple bands that represent different kinds of lineages of organisms that are very narrow, and then they start to get wider and wider as we start to kind of get into the Cambrian. And that width is supposed to represent the number of different kinds of organisms that were evolving during that period of time. You can also see that the width of those purple bands doesn't continue to get wider without interruption throughout the Phanerozoic Eon, but there's times where it's pinched as well, and those pinched times represent different mass extinctions that have occurred throughout the Phanerozoic Eon. And so there's one, kind of the first one is kind of at the end of the Ordovician, and we'll talk about that more in a minute. But anyway, there's lots of fossils that date from this period of time, the Cambrian explosion. Conodont elements are a famous Cambrian period fossil, and they are these little fossils that are shown in the top right of the slide, and they look like teeth, but we know now that they're actually not teeth. They're kind of the internal structures of these, what we think were eel-like organisms. So here's a picture of the kinds of conditions that would have been present throughout the Cambrian. We already mentioned that these are very conducive to life because the warming Earth created a situation where there was lots of shallow, warm seas. So the light blue areas on this image of the Earth are supposed to represent areas where the ocean has come up over the kind of continental geologic material to create these thin, shallow seas, and so we call these Epi-continental Seas. So epi meaning, right, like the skin, the surface of the continents, and these are some of the kinds of environments where all this life would have been exploding. So as we continue into the Paleozoic, we learned that towards the end of the Ordovician period, there was a mass extinction, and then after that period, the life gets kind of back on track and starts to expand again. And it expands again with another period of warming, and this is usually attributed to, increased greenhouse gases in the atmosphere. And also, this is the time in the Earth's history when land plants start to evolve. So plants and algae had already existed in the ocean for quite a period of time now, but this is when they start to come up into the terrestrial environment, and then they also start to expand into all this new territory very quickly, and also evolve very quickly to take advantage of all these new kinds of ecological niches. So kind of the latter half of the middle part of the Paleozoic era is a period that's called the Carboniferous period, and sometimes this is broken down into the Mississippian and Pennsylvanian periods that you'll see in some diagrams. But during this period of time, there was a big buildup of plant material in these terrestrial environments that wasn't breaking down. And these plant materials that were coming up onto the land were kind of evolutionarily a step ahead of many of the kinds of bacteria that break plant materials down today. So these land plants were starting to evolve certain cell types, like lignin as a type of cell. You don't need to know that term for this class, but it's a type of cell that's really tough that makes up the woody parts of plants. So plants were evolving this new cell type to live on land, but bacteria hadn't really figured out how to break that down very well yet. So there's this kind of offset for a while where plants are growing and dying and bacteria aren't able to break them down really successfully, nor are fungi able to break them down very successfully. But then also the warm earth at this time had a lot of these kind of shallow, warm seas and these kind of swampy environments where plants were dying and then landing in aquatic environments. And organisms don't break down if they die in water nearly as fast as they do if they die in places where they're exposed to the air. That's because there's a lot less oxygen in the water, so bacteria that depend on oxygen can do their work much more slowly in these wet environments. And so this was another reason that we theorize we have a big buildup of plant material from this time is because there was so much plant material that was living and then dying and then not decomposing very quickly in these kind of warm, swampy, coastal environments. And so a lot of the fossil fuels that we mine and use today for energy date back to this period of time. And in particular, coal, we know, is a material that is created and has its origins in these land plants. So some of the other fossil fuels like natural gas or oil are created from more marine organisms, but the land plants are really responsible for creating these big coal reserves. Okay, so we continue on through the Paleozoic era, and the very last period in the Paleozoic era is called the Permian, and it was during the Permian period that the famous supercontinent Pangaea started to form. So throughout all of this time, just like throughout most of the history of the Earth, plate tectonics have been moving the continental masses around. And about 290 million years ago, which is during the Permian, the orientation of the plates was such that most of the land mass was joined into one large supercontinent. And so you can see in this diagram, where the parts of North America would have been, South America, Africa, Antarctica, India was disconnected from Eurasia, Australia, etc. And obviously we've talked about Pangaea quite a bit before in our discussion about plate tectonics and other things. But this smashing together is famous in the United States for creating the Appalachian mountain range along the East Coast. So this period of time would have been after 10 p.m. on our geologic clock, and the formation of Pangaea is kind of the most notable thing from this period of time. Okay, so that brings us then to the beginning of the next era, the Mesozoic era, and that would begin almost at 11 p.m. on our 24-hour clock, more like 10:53 p.m. And the Mesozoic era starts off with the continents formed into Pangaea, and it is broken down into only 3 periods, so a little easier to remember than the 6 periods of the Paleozoic. And the periods are called the Triassic, then the Jurassic, which is the most famous period name that most people have heard of, and then finally the Cretaceous. So we'll talk a little bit about those next. Oh, I guess I should mention this is 251 million years ago, the beginning of the Mesozoic era, and it ends 65 million years ago. Okay, so the first 2 periods are called the Triassic and the Jurassic, and we mentioned that at the beginning of the Triassic, the Pangaea had already existed because it had formed during the mid-Permian, and it lasts through the Triassic and into the early Jurassic period and breaks up about 200 million years ago. So it was existing on the planet for about 90 million years, which is a pretty long time. And it broke up through continental rifting, so this is a process that we also talked about when we were discussing plate tectonics earlier on in the semester. We learned that heat rising up into parts of the Earth from the mantle leads to convection that causes continents to crack and split apart, and different parts of continents to move in opposite directions as ocean basins are created in between them. And so in this case, several different ocean basins were formed, and most notably the Atlantic Ocean was formed and opened up as the kind of western part of Pangaea and the eastern part of Pangaea separated from one another. Along with time, as the Americas start moving away from the other parts of Pangaea, there is an active subduction zone along the western part of North America. And so that western part of North America is experiencing subduction, and many island chains that have been formed out in what we think of as the Pacific Ocean today were being kind of moved on a conveyor belt essentially towards western North America, were slamming up against North America, and were being what geologists call accreted on, or basically stuck on to the west coast of North America, and we're starting to build it out towards the west. So 200 million years ago, areas where we live in Plumas County would have been coastal areas, and all the other parts of California, as well as other coastal portions of Mexico and Oregon and Washington, etc., were not actually part of North America at this particular time. So it's kind of a geologic perspective. And then, of course, most famously, both of these two periods, the Triassic and Jurassic, were periods of time when dinosaurs were starting to roam the planet. So dinosaurs during the Triassic were smaller, they were just starting to evolve, and it wasn't really until the Jurassic that we started to get a lot of the kind of more famous, bigger sized dinosaurs. And actually most of the most famous dinosaurs didn't exist during the Triassic or the Jurassic, but actually weren't in existence until the next period called the Cretaceous, that started about 144 million years ago. So for instance, T-Rex, figured down here on the right side of the slide, is actually a Cretaceous period dinosaur, not a Jurassic period dinosaur. So Hollywood got that one wrong. Okay, so as we get into the Cretaceous, we mentioned there's a lot of these big famous dinosaurs roaming around the planet. It's a relatively warm period, and we know warm periods are associated with rising sea levels, where ice and glaciers are melting, seas are expanding, coming up on top of continents, creating more epi-continental seas. And so you can see on the right-hand side of the slide here, we have in North America a huge interior seaway where the ocean was actually covering land all the way from Canada all the way down, connecting it to the Gulf of Mexico below. And so a lot of the area in like the Southwest or in the Montana, in the Dakotas area, actually would have been underwater during this period of time. And there's some evidence of that based on marine fossils, as well as different kinds of rocks like limestone that exist in some of these areas dating to this time, that we know only form in marine environments. So the seas reached their highest level in about 200 million years in the Cretaceous. And as we discussed, there's also a lot of subduction that's going along on the west coast of America. So the Sierran Arc forms, and that was that range of volcanoes that was created by the subduction of the Farallon plate that we've talked about a few times. So a plate that was subducting underneath California at that period of time was bringing down volatiles, creating magma, and creating volcanoes. And we walk around on the old magma chambers, or plutons, that are created from the evidence of that past magma. So that was going on between about 120 and 80 million years ago. And then more recently than that, there was a shift in the angle at which that Farallon plate was subducting. So while it was subducting in the period of around 100 million years ago to create the Sierran arc, it was subducting at an angle that was a little bit deeper. And then maybe because of a change in the rate at which it was subducting, it started to kind of be buoyed up around 80 million years ago. So the diagram on the right, as compared to the left, shows this plate subducting at this more shallow angle. And as it did this, instead of creating magma near coastlines, because it was not getting as deep, so it wasn't as hot, wasn't creating as much magma, it was creating drag along the bottom of the continental pieces that was actually cracking the continent and creating these big faults. And then the rocks on opposite sides of faults were kind of moving up and down with respect to each other. And that is responsible for the formation of the Rocky Mountain Range, which is actually made up of many different mountain ranges that exist kind of in the area stretching from, Colorado all the way up into Canada. So you can see there's some black lines supposed to represent fault lines that are being created to allow the buildup of the Rocky Mountains during what was called the Laramide orogeny, right? Remember, orogeny means a mountain building event, and so the Laramide orogeny is a name for this kind of series of events or a period of time where these Rocky Mountains were building up. Okay, so that brings us to the end of the Mesozoic era, and the end of the Mesozoic era is pretty famous or infamous in geologic history. It's often referred to as the KT, Mass Extinction, K standing for Cretaceous. You would know Cretaceous is spelled with a C. That was already taken up by Cambrian. This period of time, which would clock in at about 11:52 p.m. on our 24-hour clock, so relatively quite recently, corresponds to a period of time 65 million years ago. And this time is famous to geologists and paleontologists and biologists because there's this really rapid shift or change in the fossil record that occurs at this time. So many organisms that existed before 65 million years ago very abruptly disappear from evidence in fossils in different kinds of sedimentary layers around the planet. And so whenever we have a huge drop-off in the kinds of fossils that exist, we know there must have been a huge drop-off in the number and types of organisms that existed at that period in the Earth's history. And so we refer to these events as mass extinction events. And this mass extinction event, 65 million years ago, is the most recent one that has occurred. And it famously wiped out all the dinosaur species, as well as 90% of all the plankton species in the ocean, and 75% of all the plant species on the planet. So obviously that's a huge shift in the kinds of life that are existing on our planet. And there's kind of two competing theories about what was the main driver of this mass extinction event. And we know that both of these things certainly occurred, so it's just kind of trying to understand how responsible each of these events is for how many of these mass extinctions. And kind of the most recent thing that I've read about this is that, it's probably some of both. So we know, first of all, that there was a very high period of volcanic activity that occurred. We mentioned earlier when we were talking about basalt flows, the Deccan Traps is this period or this location in India where there are these huge basalt flows that are associated with kind of hotspot volcanism in that region. And that, as well as other volcanic activity, would have introduced a lot of greenhouse gases into the atmosphere that would have warmed the planet considerably. And so we think a lot of those large-sized dinosaurs were dying off as there was starting to be a shift in the climate in the planet. And then, to add insult to injury, there was a 10-kilometer wide meteorite that came from space and slammed into the Yucatan Peninsula. So 10 kilometers, that's about 7 miles wide. That's a huge piece of rock to slam into the earth. And it slammed into the earth in a place where some of it hit land and some of it hit water. It was kind of right along this coastline. And so as it hit land, it threw an enormous amount of debris from the landscape and from itself, smashing apart up into the atmosphere. And that would have created so much dust and debris in the air that would have completely blocked out the sun and made it pitch black. And in many estimates, it may have been pitch black for months with no sun getting down to the ground, which you can imagine would kill many plants and other organisms that depend on that heat from the sun. There was also so much particulate matter in the air that the water that was falling through the air as rain was mixing through some of those materials and then coming down to the ground as an acid. So there was acid rain falling in this pitch black, dark environment. And because some of this meteorite landed in the water, it set off a massive series of tsunamis that traveled around the planet and was very devastating to all these coastal communities. So we already had an environment that was being vulnerable because of this fast climate change that was occurring before the meteorite hit. So probably some species were dying out as a result of that. And then there was this hugely devastating impact that occurred 65 million years ago. And that was kind of the 1-2 punch that led to this mass extinction event. So, after this mass extinction event occurs, we start on the last era that we're going to talk about, the Cenozoic Era, which, again, began after this meteorite impact 65 million years ago and is still existing today. So we live in the Cenozoic Era. As we already mentioned, this would start about 11:50 p.m. on our 24-hour clock. And we know that there's a lot of geology that's still happening today. So there is some interesting things that have occurred in the past, like the formation of the Alpine Himalayan chain, which is this kind of series of many different mountain ranges that exist all the way from Europe through the Middle East and then into Asia, stringing together the Alps in Italy and Switzerland and France, all the way over to the Himalayan region in China and Tibet, Nepal, Pakistan, etc. And so that kind of occurred early on in the Cenozoic Era, that most of those mountains date to about 55 million years ago. And then much more recently, there was more mountain building in the western United States, closer to home, where the Basin and Range province opened up. And so on the map on the lower part of the slide here, you can see the Rocky Mountains that are shown in kind of darker black towards the right hand of the slide, and then the Sierra Nevada Mountains that are shown in the area where we live, closer to the west coast. And then there's this expanse in between them, and that expanse is a whole lot wider than it was during the time when the Sierra Mountains formed and when the Rocky Mountains formed that we talked about on the last slide. And so this area has actually been stretching out for the last 17 million years as a result of convection heat rising up in this particular spot. And as the Earth has been stretching, we talked about in our discussion of earthquakes, it's been cracking, and then there have been motions along these faults where some of the rocky landscape is moving up and some of it sliding down kind of in between and creating these alternating layers of basins and ridge tops. That's called the Basin and Range, or the Great Basin province of our country. And anyway, that geologic process, that stretching and the cracking and then the faulting kind of in these vertical directions, is a relatively young geologic process. Again, that's only been occurring for about the last 17 million years. So the Cenozoic era was traditionally broken up into the Tertiary period and the Quaternary period. And so we already talked about the KT mass extinction, separated the Cretaceous from the Tertiary periods. However, that term tertiary has kind of gone out of style, and there's actually new terms called the Paleogene and Neogene that occur during the Tertiary period, or what we used to call the Tertiary period. So it's good to know those new terms, but it's also good to know the old terms because those are still commonly thrown around a lot. Unlike the other periods that we have talked about so far, because we know so much more about what went on in more recent history, geologists spend a lot of time further breaking down the time, most recently into the kind of smallest unit of time that's called an epoch. So that word E-P-O-C-H is pronounced epoch. I tell students it kind of rhymes with Tupac if you're trying to remember how to say it. So the epochs that occurred during the Tertiary period, now called the Paleogene and Neogene periods, are known as the Paleocene, the Eocene, Oligocene, Miocene, and Pliocene. So you may have also seen terms like that on geologic maps, maybe when you were researching for your research papers, etc. Okay, so we talked about a lot of the things that would have been occurring during those epochs, like the formation of the Alpine Himalayan chain, like the expansion of the basin and range region. But that brings us up to the Quaternary period, which would start about 1.8 million years ago. And the Quaternary period is broken up historically into two epochs. The first one known as the Pleistocene and the second one known as the Holocene. And the Pleistocene epoch is essentially the period of time that we more informally refer to as the Ice Age, which is really many ice ages and or what we call glacial and interglacial periods, where the Earth was warming, glaciers were melting, and then the Earth was cooling, and glaciers were expanding and creating these ice ages. So if we look down at this temperature graph going back 800,000 years, we can see that there's been a lot of fluctuation in the global temperature, and so you can see that there would have been warm periods where the temperature was warmer, again called an interglacial period, and then times when the Earth would have been colder. Those are like the true ice ages, the glacial periods, and those were kind of oscillating back and forth throughout the Pleistocene. So this is also the period of time when modern humans originally evolved. So we had kind of humanoid organisms that lived on the planet earlier than this, dating back millions of years, but kind of anatomically modern Homo sapien, subspecies sapien, kind of real humans that we would recognize, came about only 200,000 years ago. So that's, of course, really recently on our 24-hour clock, 11:59 p.m., and was during this Pleistocene epoch. Other famous things that are going on during the ice ages was the kind of expansion of some of these really large, what we sometimes refer to as megafauna, so big animals, things like the woolly mammoth, things like the saber-toothed tiger. There are these giant land sloths and many other these really large-sized terrestrial organisms that you've probably seen at least pictures of, or representations of in different books or online over time. So as the Pleistocene epoch ends, we have something called the Holocene epoch, which starts at the period of time that geologists and climatologists refer to as the last glacial maximum. So basically, if we look at our climate graph, the last low point on the graph represents the beginning of the Holocene epoch. So we've been warming up ever since then. That period of time is about 10,000 years ago. And this current warming period is when humans really started to get a solid foothold on the earth. We started to manipulate landscapes through agricultural production, agricultural revolutions, and other technologies that we'll talk about later on. And so the presence of humans and the presence of this warming trend is really what characterizes this Holocene epoch. So that brings us to a relatively new epoch that was only officially formed a few years ago, and this was debated for a while before it was officially named, but now, again, it's official, and we live in something that's a geologic epoch that's called the Anthropocene. So anthro, you may or may not know, is the root that means man. So this is basically the period of time that's influenced by man. And so when geologists were trying to decide whether the Anthropocene was really worthy of its own name or not, they spent a lot of time thinking if sentient, or intelligent beings in some future time when humans have gone extinct would be able to look back on the planet and look into the geologic record, look into the layers of the ground, and pick out things that were really distinct from the period of time when humans were living. And there's a variety of things that geologists felt that, yes, these future intelligent beings would be able to see. And so as a result of that, they basically started to acknowledge, or decided to acknowledge, that, yes, we are really actually in a unique geologic epoch. And some of the things that geologists and other scientists think that we are doing to leave a permanent mark, not only on life on the planet, but actually on the geologic record, are changes to the way that sediments are being distributed around the earth because of the way that we practice agriculture. So plowing and clearing of a lot of native vegetation to create these big monocultures where we're just growing one crop lead to rates of erosion that are much, much, much faster than natural background levels. So we have these rapid rates of sediment that are flowing into a lot of low-lying water bodies around continents. And then those sediments are filled with concentrations of certain types of pollen that are new, right? Things like wheat or rice or corn, things that we cultivate, are spread all around the world and are found in sediments almost everywhere at this point. And they're very, very similar all around the world because of the way that we have distributed and decided to grow these different crops. So we think that's something that will really be obvious in the future sedimentary record. We also know that the way that we practice mining is changing the way that sediments are being deposited in different places, and we think that will leave a permanent and visible change to the geologic record. Other things include radiation that's related to things like the explosion of atomic bombs that humans are responsible for. So this high presence of kind of radioactive fallout from these kinds of explosions will be captured, and we think will be a very distinct marker in the geologic record. And it's actually the beginning of the time when we started to experiment with these atomic bombs that geologists have decided on to be the real beginning of the Anthropocene, because we think that will be such a distinct marker in the geologic record. But an additional thing that we think will also be obvious in the future is that we are experiencing, or at least on our way to experiencing, another mass extinction event. So this is sometimes referred to as the sixth extinction, because there have been 5 previous noted mass extinctions throughout the geologic record. And humans are so quickly and dramatically changing the landscapes around us, as well as contributing to the warming of the climate in such a dramatic way, that we know we're losing species very, very quickly. And there's some debate about exactly how quickly because we don't actually know how many species there are to start out with, but some conservative estimates guess maybe about 30,000 species are being lost per year, which is a lot. And so we think, in the future, again, as we look back and look at sedimentary layers from, 50 years ago or 100 years ago compared to 100 years from now, there'll be a really distinct shift in the fossil record that points to this kind of really massive extinction event, and that will be something that will be notable and obvious and qualify us for actually being part of a distinct geologic epoch, again called the Anthropocene. So anyway, there's an interesting quote that I got from a Smithsonian article that I thought was kind of interesting, and I thought I would read for us to reflect a little bit about what it means to be significantly impacting our planet so much that we actually can have a new geologic epoch named after us. And this article says, 2 billion years ago, cyanobacteria oxygenated the atmosphere and powerfully disrupted life on Earth. So we know that some mass extinctions in the past have been created by shifts in life in the past. But, the article says, the cyanobacteria, didn't know it. We are the first species that's become a planet-scale influence that's aware of that reality. So we're having also the ability to dramatically influence the world around us, and we know that we're doing it. And so this article says, so that distinguishes us, and perhaps, and in my opinion, distinguishes us in our responsibility to make sure that we're not shifting the planet in such a dramatic way that we're making it untenable for other life forms and also ultimately for ourselves. And so this is something that, of course, people that think about climate and think about environmental issues spend a lot of time thinking about. We know that we have an influence on our planet. It's not possible to stop that or realistic to stop that. But what can we try to do to limit the kinds of shifts that we're experiencing in a way that we're, again, not harming so many other organisms so dramatically, and also in a way that's ultimately coming back to have negative influences on us. So some things to think